Again, my name is Glen Leverich. I'm a geomorphologist, geologist with Stillwater Sciences, and over the last couple of years, had a really great opportunity working with my colleague Zoe and Bruce Orr in some really fascinating systems throughout the entire West. Really come to appreciate systems in more arid settings of Arizona and Nevada, the Upper Gila, Lower Gila, and the Verde. Interests very much, and so we've applied many different kinds of techniques to adequately characterize those biophysical factors that Zoe had mentioned. And so me being a physical scientist, I get to focus on hydrology and geomorphology. And there's certain available and some modifications to novel tools to characterize those hydrological components that are so dynamic but so very important in the planning process and in the evaluation process of any sort of watershed management project or riparian restoration plan. And so I wanted to share with you two, I think, novel but kind of simple analytical tools that we've used to characterize hydrologic conditions. And I do have to acknowledge my co-authors, collaborators. The two examples that I'll be sharing with you today, one is from the Upper Gila, and we'll dig deeper into that relative elevation groundwater estimation approach that you saw in Matt's talk and Zoe's talk. And then the second case study is more about detecting changes in downstream flows. It's an ongoing study that we're currently working with the nation. So hydrology is inherently stochastic in systems, and the two case studies are unregulated. So they're very complex, and it's very important to understand that foundation. And again, planning for any sort of watershed management project, riparian restoration project, what are the, as Pat, you alluded to, what are the scour potential changes? What's the suitability for plantings? What sort of effect are you having on downstream flows? These are the kind of questions that we are trying to answer a lot. So let's go right into the first case study for the Upper Gila. We presented before our approach to using biophysical information to characterize the processes that can directly influence the suitability of riparian restoration. Sean Stone is going to be talking later today. I encourage you to check out his talk. We'll get deeper into what they are actually implementing. And Peter referenced earlier the Upper Gila project. One component that I want to share with you today is how we estimated the availability of shallow groundwater. It's a critical component. I'm not a botanist, but apparently plants need water, and they like it when it's near the surface. And so when they come and ask me, well, what sort of techniques can we use to estimate that? And one of the key challenges here on the Upper Gila is we had about 53 miles or so of river. We can't possibly instrument that thing with piezometers, wells all over the place. So what else can we do? What's another really reliable, cost-effective approach? And so let me zoom in here. Peter already used this location in his talk earlier today. So we're in eastern Arizona along about a 53-mile or so stretch of the river. Broad, alluvial, floodplain, valley floor. This was an enclosed basin for many years and opened up. So you've got about 3,000 feet of alluvial material in here. What is the distribution of groundwater, shallow groundwater? This is an unconfined system. We know the existing camera screw here is utilizing shallow water and surface water. But we want to understand for suitability evaluation for active restoration and planting. We want to understand that distribution throughout the riparian corridor. So now I'm just zooming in on about 1 or 2 miles of river. We applied this approach for the entire stretch. LIDAR, can't say enough about it. LIDAR is magic, and it's such an important tool. Matt mentioned this in his talk. So did Zoe, for $30,000, which sounds like a lot of money, you get an enormous amount of information. And with that LIDAR, on this project, we've worked with Utah State to collect that information. We have a vertical accuracy of 8 centimeters, horizontal accuracy of 15 centimeters. That's quite impressive. Over 100 miles or so of river, very useful for evaluating the topography, canopy height, vegetation create point clouds and so forth. So it's very, very powerful. For this application, for estimating availability of shallow groundwater, we created a contoured map based off the low flow channel that was present during the flight in fall of 2012. And I'll describe a little more. I know you've seen this twice now in different talks, but we'll describe in more detail. The contours here, the blue is the low flow channel, and the warmer the colors, the higher you are above that elevation. And so our hypothesis, if you will, is that the water table should be at the same level as that low flow channel. We need to test that hypothesis a bit. And fortunately we did when our collaborators from Desert Botanical Garden and Sean Stone and the Watershed Partnership have continued to install a few more piezometers. Here's a location where two paired piezometers, these are essentially PVC pipe that are screened, driven down into the alluvial material, and manual measurements of groundwater can be made, established. So there were 19 total to date. We want to compare. Hopefully what we're seeing is the depth of water measured in the piezometers is equivalent to what we're seeing from the relative elevation. And here's a comparison plot. On the x-axis is the 19 piezometer wells where actual physical measurements of the shallow groundwater table have been made. And on the y-axis are those depths. In blue are the actual depths, and actually there's been several repeat measurements. Sean and his team going back out, and so what I have reported here are the median values. And then in red is the associated relative elevation value at that location. So there's two types of variability that you see. Well, one, you see pretty good agreement. I'll show you a bit more proof of that next slide. You see variability from one well to the next. You also do see some differences, either overestimation or underestimation. But overall, the mean difference we're looking at is where the overestimates cancel out the underestimates. So this is showing us some confidence that using LiDAR-based relative elevation contours to estimate availability of shallow groundwater over 53 miles of river is a very good tool for restoration. This is just a comparison. We're trying to establish the regression test how well we think they compare to one another. And it has a fair fit. So relative elevation is along the x-axis, and the y-axis. Fit about a r squared of 0.69. So it's a fair fit. So we feel again this is a very good approach. It also other information that's gleaned from this is that there isn't a longitudinal variation or a lateral variation in water table. It is a water table that is parallel to the river channel. In other systems, what Zoe was talking about, on that application, we did detect there was a geologic control where they were not parallel. So we had to adjust our approach here. The other value, and I'll speak through this very quickly, this is more Zoe's work. The other value of the relative elevation data and information is Zoe was establishing the frequency of occurrence of certain native vegetation types related to the relative elevation value. So on the x-axis of both these plots, we have the relative elevation of the low flow channel getting higher up, and then this is the frequency of occurrence of cottonwood willow. And then from that, Zoe and Carly and others created essentially a conceptual model characterizing the existing distribution of vegetation with respect to relative elevation of the low flow channel. So a very, very powerful planning tool. And so in summary, again, LiDAR is great, and this approach, we have very good confidence that it's very useful. We've used it many times in other systems, and with slight adaptations, it continues to be useful. So I encourage others to use LiDAR, and this approach can be and I should say too that Sean is continuing to monitor groundwater levels I don't expect that we'll ever see changes in the water table correlated with the removal of cameras, but that is something that they will be getting that information. Okay, so the next case study I wanted to present another hydrologic tool. This is more in progress. We're currently still deeply involved in this analysis, is in detecting changes in downstream flows. The Nature Conservancy of Arizona in the Verde Valley has implementing various flow conservation projects, water enhancement projects, mainly working with the ditch companies, the diversion companies, to try to get more water back in the river. Chip Norton's here, Schrank, and the others are here who know a lot more about this than I do. And they came to us and they had a simple question of, are there differences, or is there a change in downstream flow over time, and does it, and this is the hard question at the end, was, does it correlate to when we started implementing some of these water conservation projects? So that's simply stated, but it's a very complex question. If you've ever constructed a water budget or tried to attribute certain changes in the water budget to certain processes or activities, you understand that that is very difficult. But our first and foremost question was, can we detect any changes in downstream? So this is a quick overview of where the Verde Valley is in central Arizona. And we, again, first we had to do was evaluate the suitability of available stream flow data. We weren't going to actually collect information. We wanted to first see, can we use existing USGS stream flow records for this analysis? And our hypothesis was, yes, we could. At least that was our hope. And can we detect changes in the downstream flows? And then can we assess any sort of causative effects on downstream flows? And that, of course, we are very much in progress with that. So the answer to that is, we'll see. Okay. So using available stream gauge records, fortunately, there are long-term stream gauging stations. This is upstream going down to downstream through the Verde Valley. Upstream gauge at Clarkdale. Then we have long-standing gauges on key tributaries of Oak Creek, Wet and Dry Beaver Creeks, West Coast Creek, and then this is Camp Verde on the main stem. We needed to establish some boundary conditions. Essentially, we're applying a before and after control impact statistical analysis. We focused on low flow conditions between water years 1990 and 2015. A lot of TNC's projects and other groups within the watershed have been implementing water conservation projects since about 2010. So this time period, this contemporary time period, straddles that pretty well. With a little more bias toward before 2010. And then we want to compare observed and predicted flows to discrete shifts in downstream flows. So we are going to essentially look at how the upstream contributions relate to the downstream. What are these predicting, and what are we actually observing at the downstream gauge? We had to determine what the low flow threshold was, and this is going to be simply done by looking at the exceedance curves for daily mean flows for each of those gauges. Simply, I don't need to get too much into details of this, but daily mean flows and their exceedance curves, you can see a bend in each one of these curves. Anything to the right of that, this is discharge on the x-axis. Anything to the left of that, we identified it as a threshold for low flow. So we only considered those days in hydrologic record, 1990 and 2015, where flows for all gauges were lower than their thresholds. But we also did identify that, we figured out why Dry Beaver Creek is called Dry Beaver Creek. And that is because it's dry a lot of the time. And we determined that, this just doesn't have enough data here. This would kill the analysis, so we threw it out. It's not contributing to low flows. It experiences flows, but it doesn't. Okay, so then we compared those four upstream gauges to the downstream gauges, comparing the observed to the predicted. Some fancy graphs here, but essentially we're trying to get the regression, the comparison, and compare any changes in what we predict from the upstream gauges to the downstream. So we also then try to evaluate ways to improve the fit. And so we already applied the low flow criteria. And then we noticed in the regression, it's not shown here, but we noticed in the regression there was a sine wave. And I, working with our statistician, I recommended that it was a seasonal component. So we adjusted that. We added a periodic season term to adjust fit, and that did in fact improve our R squared considerably from 0.68 to 0.78. We also then added, we tried two different additional terms, periodic season term for each water year, and then again for before and after the water year 2010, did not really increase or improve the correlation. There's another element in here too I'm not going to get into, but this is where our statistician added a component to measure the goodness of fit, the ALC criteria. So some improvement in adding those additional terms. Okay, so what we have here are the residuals, and that sounds like a ugly term, but essentially this is the trend that we're seeing in the differences between upstream and downstream flows. And so what we have here over time, okay, change, is we're seeing a decrease in that relationship, a decrease in flows, at least in the early 1990s, but overall, from 1993 to at least 2010 or 11, there's a general increase in downstream flows relative to what is being predicted by the upstream flows. The turquoise band is a 95% variability band, so any line plotted within there is statistically significant. So that increase, while it looks like it's going down here, you get a straight line going through there. So there's increasing flows downstream between 1993 and 2011 at least. Technically, could also go a straight line after that, but it could also go down. So, and then we fitted a coefficient of the water year indicator term, and that was 6.6 CFS. And so that suggests that flows have been increasing by about 6.6%. I'm sorry, CFS during this time frame. Okay, so there's increasing flow downstream. What we're currently doing is trying to understand what's happening. Is that because of flow conservation projects? Is that because of differences or changes in water uses or land uses? We don't know yet, and we've started to explore groundwater changes, population changes, water use, pumping, and so forth. And so far, what we found is none of that explains. In fact, since the wet period of the early 90s, where there was a big flood in 1993, the groundwater levels have been dropping in the wells. The population has been increasing. Overall water diversions, both combination of groundwater and surface water, have been they dropped after 1993, but then they've been steadily been increasing. So, what is contributing to this? We don't know, and we're currently trying to explore that. Let me get to wrapping this up. So, working with Kim Schoeneck and Jean Marie Haney of the Nature Conservancy, we're gonna try to further explore what is contributing to this. What is the physical explanation for this increase? Skip over that. So in summary, we were able to use available stream gauging data to detect changes in downstream flows at the scale of what we would expect for a water conservation project. So 5 to 10 CFS. That is on the order of what we would expect from water conservation. It doesn't mean that that is the answer. We certainly can't explain it by any other land use, but that gives us a good feeling about the suitability of available data from USGS gauges. I've done this analysis in other systems and come up with some other answers. So it's good to be able to use such a reliable, robust data set. And so physically, this suggests either a reduction in upstream to downstream losses or an increase in upstream to downstream depletion or some combination of there over that period of record. Again, we have to figure that out. All right, so those are two case studies. One, again, looking at estimating availability of shallow groundwater on the Upper Gila, and then the second, detecting changes in downstream flows in the Verde Valley. So that is it.
All right, thank you very much, Glenn. We have time for several questions for Glenn. I see Peter. Any other hands? All right, then Matt.
Thanks. Have you considered the possibility that there's a change in the cross-section at the discharge measuring station, like a change in the stage discharge curve? And so have you looked at that and eliminated that as a possible explanation?
Not explicitly. I mean, the grading, there haven't, I guess I'll say this, I don't expect that to have occurred. I mean, the last sizable flood for here was in 1993. Yeah, no, could it be aggregation? No, but I mean, it is, we talked about that early on, and then but that's a good point. I will say this. I will say this. It does point out, you know, the myriad processes that affect hydrology in the system. So trying to disentangle those or identify each one. But I think it's attainable. So that's what we're currently trying to work on, is essentially try to understand the water budget and the various components, and then getting to the right appropriate scale, especially with TNC projects and other computer projects. You know, I think really the answer there is going to be aligned with having to measure more closely for whatever project. It's good to see the valley-wide changes, but you're really going to need to go zero in on that local scale.
Thanks, Glenn. My voice is working. Not to add another, have you thought about this question, but have you thought about upslope conditions, and if there have been like any large-scale landscape changes on the uplands that could be contributing more runoff directly?
For the Verde? Possibly, yeah. Land cover change has increased. We looked at land cover maps, and I'm looking at Chip Norton. You might know more. I don't expect that to be an answer. Actually, one thing I do suspect is municipal water is supplied from mostly groundwater. Look at Chip and nod that, right? The cities of Camp Verde and Cottonwood get most of their water from groundwater, and then that water goes somewhere, and then it goes out of a treatment plant. And it's possible that there's some water bypassing our upstream gauges. So that's how additional water is showing up. But that's speculative at this point. But that does relate to land use. You know, right, I know, impervious cover. Most of this watershed is undeveloped.
Using your data, can you predict areas that have been historically have low water tables versus high, yet still have, both areas would have good cottonwood and willow populations? And the intent of my question is if it has historically low areas, that might suggest they've evolved rooting strategies to really go down to get that water. And so as we dry out even further, those would be the source populations that could withstand dewatering. Can you comment on that?
Not easily, no. I kind of want that's a riparian plant question, but I think when that was one of the reasons. Well, I guess I'll say this. Not only, you know, we were looking at relative elevation to understand depth of shallow groundwater and soil moisture. You know, what Zoe was looking at was really the distribution of existing native vegetation. Where are they positioned in the system? And I think you're asking.
The context of the question really comes from your astute observation that Dry Creek has little water, but yet it's still Dry Beaver Creek, excuse me.
Yeah, right.
But yet still it has a lot of cottonwoods versus Wet Beaver Creek has high water table. And so I might argue, well, let's go to Dry Beaver Creek to find our source populations for future dewatered conditions. So,
well, and I think it's important too to understand how they are being watered. They might be getting adequate irrigation runoff for our surface water. Yeah, and to point out, we had 2 case studies. We didn't do a relative elevation analysis for the Verde.
We've got time for one more question.
I just have an announcement, not a question. But the state of Utah with the Park Service collected LiDAR data for the entire Colorado River through Utah and the Green River. So that data is going to be publicly available. They're looking at accuracy of that and processing it now, but it should be available in April. So if anybody's doing any work on those stretches of river, contact the state of Utah and we can give that to you for free. So.